Okay, so in this example, we're going to solve the polynomial inequality x cubed minus x greater than 0. We'll follow the procedure by that's broken down into the 4 steps. We'll first find the equivalent inequality with 0 on one side of the inequality. That is already done, as you can see from the inequality. We have the polynomial on the left and we have 0 on the right of the greater than symbol. Alright, so then our p of x in this case is going to be the polynomial x cubed minus x greater than 0. And so basically we're trying to solve the related polynomial equation, which is x cubed minus x equal to 0. To solve this, we could factor out an x, leaves behind x squared minus 1 equal to 0, and x squared minus 1 is a difference of squares, so we could factor that as x minus 1 times x plus 1 equal to 0. Okay, so that tells us our solutions are x equals 0, x equals 1, and x equal to negative 1. Alright, step 3. Use the solutions to divide the x-axis into intervals, then select a test value from each interval and determine the polynomial sign on the interval. Okay, so I like to do like a little number line chart, and I like to specify my zeros on there. So here we'll have negative 1, 0, and positive 1. And then what we do is, well, look at the sign value of the polynomial p of x, which once again is x cubed minus x, on test values that fall in each of the 4 intervals that you see here. So our first interval O is going from negative infinity to negative 1, negative 1 to 0, 0 to 1, and then 1 to infinity. So we know at the x values of negative 1, 0, 1, we know that it's not positive or negative there, it's 0 there. And so I like to put a 0 just to remind me those are the zeros of the polynomial. And then I choose a test point, so something to the left of negative 2, or any value in the interval from negative infinity to negative 1. So I'm going to choose negative 2 there. And in the interval between negative 1 and 0, choose another test point. I'm going to choose right in the middle there, negative 1/2. And then between 0 and 1, I'm also going to choose positive 1/2, the number right in the middle. And then from 1 to infinity, I'm going to choose positive 2 again. Okay, so let me rewrite that there. Okay, so then now we plug those test values, right? The ones that I have here, these test values, into the polynomial. So I'm going to plug in negative 2. So we're going to get negative 2 raised to the 3rd power minus negative 2. So we're going to get negative 8 plus 2, which gives us negative 6. And so on that side, the interval from negative infinity to negative 1, since polynomials have no breaks or jumps, it's nice and continuous. We get negative, 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 up to negative 1 there. And now we want to see what happens between negative 1 and 0. In fact, we could kind of think based on the multiplicity that at negative 1 the graph of the polynomial would have to cross through that, so it's probably going to be positive because it has multiplicity 1 and it has to cross the x-axis there. However, we just to be sure, we can plug our value, test value in of negative 1/2, so we get negative 1/2 cubed minus negative 1/2, so we get negative 1/8 plus 1/2, adding negative 1/2 to negative 1/8, we get 3/8. Likewise, we get plugged in, so we know there between negative 1 and 0 we have positive, 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 because 3/8 is a positive value. Alright, now we can plug in our positive 1/2, and we're going to get 1/2 raised to the 3rd power minus 1/2 equals 1/8, positive 1/8, minus 1/2, and this time we get negative 3/8. Okay. All right, so then we get polynomial of 2. So we have 2 to the third power minus 2. So we have 8 minus 2, which is positive 6, and it's positive. Okay, so between 0 and 1, we know that it's negative, as we would expect, since at 0 has a multiplicity of 1, and so it has to cross and from above the x-axis and go through it, and below the x-axis are negative y values, so we can see it's negative. And then from 1 to infinity, we got an output of 6 there, so we know that it passed through the x-axis again, but this time crossed up and got positive y values there. Okay, so now next step is to determine the intervals for which the inequality is satisfied, and write interval notation or set builder notation for the solution set. Include the endpoints of the intervals in the solution set if the inequality symbol is less than or equal or greater than equal. We don't have to worry about that here because we had to strictly, we were interested in solving the equation x cubed minus x is greater than 0. All right, so the polynomial is positive on the intervals negative from open interval -1 to 0, and the open interval from 1 to infinity. Thus the solution set is the union of -1, 0, union the 1 to infinity. So it's the union of those two intervals, or in set builder notation, this is the set of x such that -1 is less than x and x is less than 0, or x is greater than 1. Okay, so we're gonna, that's how you would solve this algebraically. Now let's take a look at, say, Desmos and see how we could solve this polynomial equation or inequality using its graph. So once again, we are looking for when this is greater than 0. Okay, so we basically want to see the portions of the graph that are above the x-axis. And you can see if we just zoom in a tad here, this is the graph, and we know that the zeros were -1, 0, and +1, so you can see the intervals there. All right, so the part of the graph that's above the x-axis would give us positive outputs. In other words, positive y values or p of x values. Okay, that's because it's above the x-axis. So we know that from -1 to 0, that interval there would be the interval that would make the polynomial positive. And then the other portion of the graph of where it's above the axis is from 1 to infinity, right? If you go this way, the portion of the graph is above the x-axis, therefore the y values of each order pair are going to be positive, and you can see that as I'm tracing the graph there. And so you get to the same conclusion as we did algebraically. Of course, this is a lot more efficient if the graph is clear and easy to do. However, if you don't have a graphing, if you can't graph and you're asked to do it algebraically, then that's the way you would approach it in the previous way I showed you. All right, that's it for this video.